Hello, grade 10s. In today's lesson, we are going to continue with a section on the periodic table. First of all, let's summarize all the information that we now understand based on period numbers and group numbers and valency and valence electrons. We're going to put it all into the periodic table. So the first thing that we need to recall is that the period number, that is the row number, corresponds to the energy level in which the valence electrons exist. Each period starts with an element whose electrons are in a higher energy level. So in period 1, we have elements hydrogen and helium, and their outermost electrons exist in n equals 1. And in period 2, we have the elements lithium to neon, and their outermost valence electrons exist in n equals 2. Remember that each period in the periodic table starts with an element whose electrons are in a higher energy level. So if we look at hydrogen, well, hydrogen's outermost electrons are in n equals 1. And when we start the next period that begins with lithium, lithium's outermost electrons are in n equals 2. And when we start the next period with sodium, sodium's outermost electrons on n equals 3, and that would then apply to the entire period all the way from sodium to argon. And let's just keep in mind that the bottom two rows that make up the F block, elements 58 to 71, are part of period 6, so their outermost electrons are in the 6th energy level, and elements 90 to 103 are parts of period 7, so their outermost electrons are in n equals 7. So what I'd like you to do is to go to your periodic table and label each period as n equals 1, n equals 2, n equals 3, all the way to n equals 7. The second thing is the group number. And the group number is so important when it comes to the next section on chemical bonding, because it corresponds to the number of valence electrons and the valency. You're going to see that we're going to use valence electrons in order to work out our covalent bonds or molecular bonds, and we're going to use the valency to work out the ionic bonds. So group 1 elements all have one valence electron, and they have a valency of 1 plus. Now, my students often ask me, why do we say 1 plus and not plus 1? Well, that is just the notation in which we represent ions. Group 2 elements have 2 valence electrons and a valency of 2 plus. We then go all the way to group 13, so we skip the D block, and group 13 elements have 3 valence electrons and a valency of 3 plus. Group 14, where carbon exists, well, they have 4 valence electrons and a valency of 4 plus or minus, because remember, it takes the same amount of energy to gain 4 electrons as it does to lose 4. Group 15 elements have 5 valence electrons, so their valency is 3 minus. Group 16 elements have 6 valence electrons with a valency of 2 minus, and group 17 elements have 7 valence electrons and a valency of 1 minus. Remember that the ions that are 1 plus, we simply represent as plus, and the ions that are 1 minus, we simply represent as minus. And then group 18 elements are noble gases. They have a full outer energy level. Helium has 2 valence electrons. Neon and argon have 8 valence electrons. So again, go to your periodic table, and I'd like you to label valence electrons and valency. And next to valence electrons, I want you to insert 1, 2, then go all the way to group 13, 3, 4, 5, 6, 7, 8. The implication is that if I ask you, how many valence electrons does iodine have? You don't have to think about it. You just tell me that it is 7, based on this number that you will insert into your periodic table the moment you get a chemistry test or a chemistry exam. If I ask you how many valence electrons does boron have, well, you just need to look at the periodic table that you've populated with all these numbers, and you can tell me that it has 3 valence electrons. If I ask you how many valence electrons does barium have, barium's over here, barium has 2 valence electrons. It's simple. The next thing we're going to do is look at the valency. And above group 1 elements, we're going to write 1 plus. Above group 2 elements, we're going to write 2 plus. Then we're going to skip the D block. Above group 13 elements, we're going to write 3 plus, 4 plus minus, 3 minus, 2 minus, 1 minus. Now remember, we drew all those atoms. And so we have proven the number of valence electrons and the valency of each of those elements. And we've done the hard work and we've understood the logic. And all of that has brought us to this moment where we can just populate the periodic table with information that we now understand the logic behind. But we don't need to go and work it out from scratch every time. So if I had to ask you, what is the valency of potassium? It's just a plus or a 1 plus. If I had to ask you, what ion does potassium make? It simply makes the K plus ion. That is the only ion that potassium can ever make. If I had to ask you, well, what ion does calcium make? It is the Ca2 plus ion. What ion does barium make? Ba2 plus. If I had to ask you, what ion does aluminium make? It's aluminium, Al3 plus. If I had to ask you, what ion does bromine make? It's Br minus. Remember, we don't include the 1 in our ionic notation. If I had to ask you, what ion does sulfur make? It's S2 minus. Oxygen is O2 minus. If I had to ask you, what ion does phosphorus make? It's P3 minus. It's really, really simple. You don't need to think about it. You just need to look at the periodic table. And we're going to practice that a lot when we do our covalent and ionic bonding. In terms of the shells, group 1 and group 2 elements make up the S block. So we then know that their valence electrons exist in an S shell. And group 13 to 18 elements make up the P block, so their valence electrons exist in a P shell. Elements in group 3 to 12, they make up the D block. And remember, those are known as transition metals, and their valence electrons are in a D shell. We're not considering the D shell. And elements 57 to 71 and 89 to 103 at the bottom of the periodic table make up the F block. Again, we're not considering the F block, but that means that the outermost electrons are in an F shell. So now we can populate the rest. So what we can do is we can label that this is the S block and this is the P block. Okay, the fact that this is the D block and this is the F block is just nice for us to know, but we don't work with those shells. And the other thing that we can add to our periodic table, just to make it complete with information, is, well, the D block, these are called transition metals. Group 1 elements are called alkali metals. Group 2 elements are alkaline earth metals. Remember that group 18 is noble gases, or also known as inert gases. And then group 17 over here, those are halogens. So all of these elements over here are known as halogens. Remember that any compound formed with a halogen, so any compound formed with fluorine, chlorine, bromine, iodine, will be called a halide. So for example, sodium chloride, well, because chlorine's a halogen, sodium chloride is a compound that is called a halide. And calcium fluoride, well, calcium bonds to a halogen, making it a halide. Then the other thing that we learned is that anything bonded to oxygen is an oxide. So lithium oxide is a compound known as an oxide, and nitrogen dioxide or nitrogen monoxide will also be known as a compound that is an oxide because it's bonded to oxygen. And that's really all the information on the periodic table that we should summarize up front that will make our lives so much easier from grade 10 to matric. So the periodicity within the periodic table refers to a property that varies uniformly with the arrangement of the elements as they are arranged in the periodic table. And there are many physical and chemical properties of elements that follow a sequence in the periodic table as we move across a period or as we move down a group. And we've seen that in terms of the N value, in terms of the valency and the valence electrons. What we're going to do now is we're going to look at how the valency corresponds to a certain type of bond known as an ionic bond. So we've noted the periodicity of elements regarding the number of valence electrons and valency. How does this correspond to the way that atoms react? And right now we're only going to consider the formation of compounds that are held together by ionic bonds. For ionic bonds, we are interested in valency. In the next section on chemical bonding, we are going to do ionic bonds again based on valency, and we're also going to do covalent bonds, also known as molecular bonds, based on valence electrons. But right now we're looking at ionic bonds. So this type of chemical bond forms when one ion becomes positively charged because it wants to give away an electron or more than one electron. And the other ion becomes negatively charged because it wants that electron or those electrons. And so now we have an ion that's positively charged and an ion that's negatively charged. And there's an electrostatic force of attraction between them. And that is what the bond is. The metal always becomes the positively charged ion, the cation. It transfers electrons to the non-metal. The non-metal always becomes the anion, which is the negatively charged ion. We need to understand that all the compounds are going to be neutral. So a compound that is formed by a cation and an anion, we need to balance their positive and negative charges so that the compound as a whole is neutral. So here's some examples. What compound will be made from the reaction of lithium and fluorine? Well, the lithium ion, if we look at where lithium exists, it is in group 1. So all I have to do is go to my periodic table and I can figure out that the ion that lithium makes is simply Li+. Now, fluorine is in group 17. So what ion does fluorine make? It makes F-. So we can fill this in as Li+. Remember that lithium can only become lithium plus because it wants to give up its one valence electron in order to have a full outer energy level. It can't make any other ion. And fluorine, or the fluoride ion, also just known as fluoride, is F-, as we just saw on the periodic table. And remember that it can only become an F- because it needs to gain one electron to have a full outer energy level. So remember that a compound, an ionic compound, is always neutral. So the 1+ positive charge of lithium and the 1- negative charge of fluorine will balance each other out. So Li+ plus F- makes LiF. This is known as lithium fluoride, which you should be able to name based on the naming methodology that we have learned. What compound will be made from the reaction of sodium and oxygen? So again, we want to just get used to always working with a periodic table. So let's go to the periodic table and figure out the ions that sodium and oxygen each make. So here's sodium. Sodium is going to make the Na+ ion. and here's oxygen. Oxygen's going to make the O2 minus ion. What is the symbol of the sodium ion? Well, we just saw it is Na+. Sodium can only become Na+. There are no other ions that sodium can make. And the symbol of the oxide ion is O2-. That is the only ion that oxygen can make, because oxygen needs to gain 2 electrons in order to have a full outer energy level. So now we have oxygen that wants to gain 2 electrons, and we have sodium that only wants to give away 1 electron. But we need to balance out our compound in order to make it neutral. So therefore, we need 2 Na pluses with 1 O2 minus to make Na2O. So if I take Na plus and O2 minus, well, that is going to form the compound sodium oxide, but within that compound, I have Na2, because I actually need 2 Na pluses to balance out the 2 minus of 1 oxide ion. What compound will be made from the reaction of aluminium and chlorine? Again, first step is to go to the periodic table and figure out the ions. Aluminium makes the Al3 plus ion, and the chloride ion is Cl minus. So the aluminium ion is Al3 plus. Aluminium can only be that ion, and the chloride ion is Cl minus. It can only become Cl minus. So now we have aluminium that wants to give away 3 electrons, and we have chlorine that wants to gain 1. So you can see that we need 3 chlorine atoms to form 3 chloride ions to balance out the fact that aluminium wants to give away 3 electrons. So we would say that Al3 plus and Cl minus, those are the 2 ions involved, will form AlCl3. This little 3 represents that we need 3 chloride ions to bond with 1 ion of aluminium in order to form a compound that is neutral. Now, there is a method that actually one of my students came up with, and I feel that it works really well. It reduces confusion and it reduces errors, but there is one exception to the crossing method that might actually cause more confusion than necessary. So take a look at this method, and if you like it, use it, but also remember the exception here. So let's look at the examples that we dealt with. So in the crossing method, I simply say, okay, well, Li plus and F minus, I have to work out my ions, but that's super simple. I go to the periodic table. Now, this plus represents a 1 plus, and this minus represents a 1 minus. So I cross the 1 to put it next to the fluorine, and I cross this one to put it next to the lithium. But of course, we don't represent compounds as Li1F1. A 1 is simply ignored, so that forms LiF. Let's look at the next one. So we've got Na plus and O2 minus. Now, what we can do is we can cross it so that the 2 moves here and the 1 moves here, but of course a 1 is ignored, which gives us Na2, a 1, but we ignore the 1, so we get Na2O. Here's the example with aluminium and the chloride ions. So aluminium makes a 3 plus ion and chloride is 1 minus. So we transfer the 1 over here and we transfer the 3 to the chlorine. We end up with Al1, which we ignore the 1, Cl3. Now this cross multiplication method can help us solve slightly more confusing examples. Like if we take aluminium and oxygen, making aluminium oxide, the aluminium ion is Al3 plus and the oxygen ion, oxide, is O2 minus. Now, aluminium can only become Al3 plus because it wants to give up 3 valence electrons to have a full outer energy level. And oxide can only become O2 minus because it wants to gain 2 electrons to have a full outer energy level. But now we need to somehow balance this. Now, the lowest common denominator is 6. So if I take 2 aluminium atoms, well, 2 aluminium atoms will want to give up a total of 6 electrons. And if I take 3 oxygen atoms, well, the 3 oxide ions will want to gain 6 electrons. So using that logic, well, we can say that we need 2 aluminium atoms for 3 oxygen atoms. But I know that this is confusing. So the cross multiplication method works really well here. We transfer the 2 from the O to the bottom of aluminium, and we transfer the 3 from the aluminium to the bottom of oxygen, and thereby we get the compound of Al2O3. Now, this is where you need to be careful if you're going to use this crossing method. If we look at a situation like the formation of aluminium nitride, the aluminium ion is Al3 plus and the nitride ion is N3 minus. If you had to use the cross multiplication method, you would go Al3 N3, but that is not the case. It forms ALN. And let's think about the logic. Aluminium wants to give away 3 electrons. The nitride ion wants to gain 3 electrons. So they only need to get together in a 1-to-1 ratio. I don't need 3 of these to balance out 3 of these. The implication here is that if you're going to use the cross multiplication method, you might get it wrong. What you need to do is, if you can simplify your ratio, so if you get Al3N3, well, you can simplify that to Al1N1, which is ALN. So aluminium nitride is ALN. Just don't forget that if you end up with a ratio of 2 to 2, you need to simplify to 1 to 1. If you end up with a ratio of 4 to 2, you need to simplify that to 2 to 1. Let's consider the formation of the following ionic compounds based on their valency. Write the ionic equation of each, meaning that you need to write the ion of potassium plus the ion of nitrogen, then an arrow, and then the chemical formula of potassium nitrite. So I suggest that you pause the video, you try to fill these in on your own just to test yourself before you unpause the video and look at the answers. So we've got potassium that makes the K plus ion, nitrogen that makes the N3 minus ion, simply from the periodic table by looking at your valency column, and that forms K3N, which is potassium nitride. Beryllium and iodine form beryllium iodide. So we have Be2 plus I minus makes BeI2. Magnesium and sulfur form magnesium sulfide. So we have Mg2 plus S2 minus. And if you're going to use the cross multiplication method, you'd get Mg2S2, but you need to remember to simplify that to Mgs. And the logic is that magnesium wants to give up 2 electrons and sulfur wants to gain 2 electrons. So you only need 1 magnesium ion for 1 sulfide ion in order to balance the compound. Barium and phosphorus form barium phosphide. So we have Ba2 plus and P3 minus, and that makes Ba3P2. Calcium and oxygen form calcium oxide. So we have Ca2 plus and O2 minus. Using cross multiplication, you'd end up with Ca2O2, but that's not how it bonds. We have to simplify that to CaO. Identify a halide and an oxide from the list above. So a halide is a compound formed with a halogen. That is a group 17 element. And an oxide is a compound formed with oxygen. So a halide would be beryllium iodide because iodine is a halogen. It's a group 17 element. And an oxide, well, that would be calcium oxide because it is an element that is bonded to oxygen. In the next lesson, which will be the last lesson on the periodic table, we will look at the periodicity of the elements based on atomic radius and ionization energy.